Freshwater Ecology presents Sampling a Wadi, starring Suleiman Al-Salmi and co-starring Omar Al-Rakmi. A Greenfish production. The objectives of this lab are to learn sampling protocols for flowing waters and learn to analyze samples from flowing water systems. Our sampling site is Freshwater at lovely Narkal in Oman. The first step is to choose your sampling site and establish a transect by running a ruler across the wadi. Our second step will be to measure the flow at 1 meter intervals across our wadi stream. As our stream is shallow and has a depth of less than 0.5 meters, we will measure flow at 0.6 meters of the depth. So this means 0.6 of 0.5 meters, we will measure at 0.3 meters. If it was more than 0.5 meters deep, we would measure at 0.2 and 0.8 meters of depth and average over the two. This is of course because the flow varies as it moves away from the bottom towards the middle of the channel. We will assume that the wadi moves out at an angle and that the edges are a shallower area. So assuming it's roughly a triangle, we will assume that each of the edges is about half the cross-sectional area of the main channel. First, we take our flow meter, which is a torpedo-shaped instrument, and with a little propeller on the end, which we face into the stream. As the water flows across, it turns the propeller. We take an initial reading before we start. For each of the 1 meter intervals that we noted before, we record the flow in the middle. We allow the meter in the water and allow the wheel to turn for 1 minute. At the end of 1 minute, we record the number on the flow meter again and calculate the difference. So for instance, before, if the number was 21506842, and afterwards it's increased to 21507305, we subtract the before from the after and we find that the difference is 463. We repeat this for each segment. We can then convert this number into a flow rate using the chart below. Remember, you measured for 60 seconds and this chart is in counts per second. Therefore, we need to divide our number by 60. Our number was 463. Dividing by 60 gives us a value of approximately 7. So it's quite slow, so we use this little insert. And reading across here, we get a flow rate of 22 centimeters per second. We can now calculate the discharge at this point of the wadi by multiplying the flow rate by the cross-sectional area. We divide the wadi into 5 segments, 3 central segments and 2 edges. So for each of these we are going to calculate a discharge and sum them together. The first segment we look at here is 0.3 meters deep or 30 centimeters, which is 1 meter or 100 centimeters wide, and has a flow rate of 15 centimeters per second. This is equal to 45,000 centimeters cubed per second, or 45 liters per second. The second section is 0.5 meters deep, so this is 50 by 100, and the flow rate is 18 centimeters per second. This is 90,000 centimeters cubed per second. The third is 0.4 meters deep, so this is 40 by 100 and a flow rate of 12 centimeters per second. 48,000 centimeters cubed, or 48 liters per second. Our edges, we're going to assume that they are a roughly triangular shape and about half the cross-sectional area of a rectangle. So the first is 30 centimeters deep times 100 and a flow rate of 10 centimeters. Dividing by 2 for our half cross-sectional area, this is 15,000 centimeters cubed. The final area is 0.4 meters deep, 40 centimeters by a meter, and a flow rate of 9 centimeters per second. Dividing by 2, this gives us 18,000 centimeters per second. We now add all of the segments together to calculate total discharge. This comes to 216,000 centimeter cubed per second, or 216 liters per second is the discharge at this particular point in the stream. The third step in the analysis is to sample the autotrophs and the organic matter. Now, unlike a lake where most of the organic matter is suspended as phytoplankton, most of the organic matter in the stream is attached to the bottom, primarily to rocks and sediments where we have periphyton and other detritus accumulating. The first step is to collect a random sample of different sized stones, which we will later analyze in the lab. The next step is to sample the macroinvertebrate fauna. We do this by holding a net in a stream and kicking vigorously. Come on, Suleiman, you can kick harder than that. The animals and other material is collected in the net and taken to a tray where it's tipped. Here the sample can be counted live and returned to the stream, or preserved in 70% ethanol for detailed counting and taxonomic analysis later. The final thing is to check the physical-chemical data, such as conductivity and temperature, As you can see from the meter, the temperature is high and the conductivity is also high because this is a hot springs. pH also is high. The system is quite alkaline. Now we have returned with our samples to the laboratory for analysis. Our first step is to determine the organic matter on the stones. Now, each of these stones we collected contains a mixture of material. Some of it is organic matter. Some of this organic matter will be living periphyton, which contains chlorophyll A. The remainder will be detritus or dead organic matter. There will also be an accumulation of inorganic matter, primarily clay and other inorganic materials. Our first step is to remove all of the organic matter by brushing the stone using a toothbrush or other brush in 200 mils of water. Come on, Omar, you can do better than that too. If you do this, you're going to have, if you brush your teeth like this, you're going to have lots of dental decay. When you have completely removed all of the material from the sample, divide into two 100 ml subsamples. For measurement of periphyton, take one subsample and filter through 100 ml through filter paper to collect the periphyton. After filtering, the filter paper is placed in a centrifuge tube with 10 ml of 95% ethanol to extract the chlorophyll and stored at 4 degrees in the dark for 24 hours. After 24 hours, it's centrifuged at 500,000 RPM for 10 minutes to remove the debris. the chlorophyll is now in a supernatant, and we're going to analyze it using a spectrophotometer. We take the sample from the supernatant and add it to a spectrophotometer tube, and we take 3 readings of the sample, one at 665 nanometers for chlorophyll A, one at 649 nanometers for chlorophyll B, and one at 750 nanometers for turbidity. Each time we zero the system with a blank to ensure there's no background. Once we have our readings, we use the following formula to calculate chlorophyll A. It is 13.7 times the reading at 665 minus 750 minus 5.76 times the reading at 469 minus 750 reading. So exactly what does this mean? Let's do an example to understand. In our example, the reading for chlorophyll A will be 0.112. At 649, the reading for chlorophyll B is 0.02, and at 750, the reading for turbidity is 0.01. We then put these into the formula, which gives us 13.7 times, in a bracket, 0.0112 minus 0.01, and 5.786 times, in a bracket, 0.02 minus 0.01. Doing the calculations, this tells us that the total amount of chlorophyll A on the subsample of stone was 0.13 micrograms. Later we're going to convert this to a density. But first, let's have a look at how we analyze the total organic matter on the stone. Now, the total organic matter will include all of the periphyton plus any dead material there. The other thing that will be on the stone will be inorganic matter, such as clay and fine stone or sand particles. So the first thing we need to do is to pre-weigh a filter paper and record its weight. We then take the second of our 100 ml subsamples that we made before the stone extract and filter it using our pre-weighed filter paper. We dry the filter paper in an oven at 70 degrees for at least 48 hours. When the paper is dry, it is re-weighed. We can now calculate the total mass of organic and inorganic material on the rock. So, for example, we have the filter paper weight before was 1.2 grams. The filter paper weight after filtering and drying was 1.9 grams. So we call before FB and after FA. The mass of organic and inorganic matter will be FA minus FB. which is 1.9 minus 1.2, which is 0.7 grams. To calculate the mass of organic matter, we now need to put the sample in a mussel furnace at 550 degrees for 2 hours. This will burn off the organic matter and leave the inorganics. When the oven is cooled, we remove the ash and weigh the remainder. We will call this FMF, or muffle furnace. Right, so now we can calculate the total organic matter using the formula Fa minus FMF. For example, if Fa value was 1.9 grams and after the muffle furnace the weight was 1.6 grams, total organic matter must be the amount that is lost, Fa minus SFM, which is 0.3 grams. This is the total organic matter. The total inorganics, glaze, etc., is FMF minus the initial weight of the filter paper. So in this case it would be 1.6 minus an initial weight of filter paper of 1.2, which would be 0.4 grams. But, and this is a big but, as you can see, a much larger font, rocks come in different sizes. Large rocks will have more organic matter than small. So therefore, it really doesn't mean much to say that one rock has this amount of organic matter and this has another, unless we can standardize for rock size. But this is not easy. How do we standardize the rock size for a complex three-dimensional object? Well, we have to use a bit of high-tech science here. We will wrap each stone carefully in aluminium foil, just like a roast potato, covering exactly the size of the stone, then weigh the aluminium. We're going to use a chart we've calculated before of foil surface area versus weight to calculate the rock surface area. So here is a chart we're using, and we simply read off. If the aluminium foil we wrapped our rock in had a weight of 1.5 grams, we can read this off and see that the surface area is 375 centimeters squared. We can now convert our results to density, but remember we initially divided the sample into 200 milliliter sublots, so we need to multiply all our rocks results by 2. For our rock with a surface area of 75 centimeters squared. Our chlorophyll A, we've calculated here, imagine 25 micrograms. So we multiply this by 2 for a subsample, and that gives us 50 micrograms of chlorophyll A on our rock. So to convert this to a ratio per surface, we take out 50 and divide by 75 centimeters per squared, and it gives us a value of 0.667 micrograms of chlorophyll A per centimeter squared. Similarly, if this rock had 0.6 grams of organic matter in our sample, it would then be multiplying by 2, 1.2 grams. So the total organic matter would be 1.2 divided by 75, which is equal to 0.016 grams per centimeter squared. The final part of the analysis is to count and identify the macroinvertebrates. This is usually done in laboratory with the aid of macroinvertebrate keys. And this brings us to the end of our movie on sampling of wadi and thawara at Nako.